so you can visibly see what.
All righty. Before I introduce our speaker, just a couple of quick announcements. First of all, if you're a student, feel free to write your name on a ballot and put it in the box. We're going to hold a raffle at the end of the talk, and you might win a prize. It'll be a copy of Dr. Palacios' book. Dr. Palacios is a graduate of TU, he's an alum. He's a graduate of the Mechanical Engineering Department, where he earned his doctorate and did, in fact, he was the first recipient of a Ph.D. In the Mechanical Engineering program at TU ever. So it's a real privilege to have him visit with us. Dr. Palacios is a corrosion expert. He's received a distinguished, a NACE Distinguished Member Award. He's a NACE Certified Specialist in Internal Corrosion as well. His career took him to to work on projects in many countries. I was also really interested to learn from him about, in informal conversation, about corrosion aspects, even in the unconventionals here, domestically in America, related to fracking jobs. Really interesting work. So without further delay, Dr. Palacios.
Thank you, Rami, and thank you for the invitation. It's been, what, I don't know, maybe 15 years since the last time I was here in Tulsa, even though my two kids were born in Tulsa, Oklahoma. But I think it was when Charlie retired. That's maybe 15 years ago, the last time I was here. So new buildings, new everything. So
Did you not invite him?
I did invite him, but anyway, I'm gonna have dinner with him tonight. But I told him to come, but he said he would do his best to come. So if he doesn't come, that's okay. I'll see him later. So, so once again, it's an honor to be here. I mean, this is my alma mater. I love this place, like you have no idea. And also I feel very proud that I see one excellent initiative from the Petroleum Engineering School, in which I am involved teaching a corrosion, a water treatment course, which corrosion is part of it. And I really think it was a great initiative because, I mean, hey, water treating is huge for nowadays and always have been. And the fact that we have this course in the curricula is an excellent initiative. I really appreciate that. So anyway, what I'm going to talk about is a little bit of my experiences throughout the oil and gas industry. My whole idea is to take you through a journey. And as a matter of fact, those of you that can get the book, I wrote the book as a journey, and it's my journey through this wonderful field called the oil industry, and especially in the area of corrosion. So that journey starts on the reservoir. Although I'm not a petroleum engineer, I think I understand a little bit of reservoir engineering just to be a little bit dangerous in what I am familiar with and what is my interest. So corrosion doesn't happen in the reservoir, but we need to know what things in the reservoir. So this is basically through the whole journey that I like to take you this afternoon. Starting with the reservoir. I will not have time to describe everything that happens from the point of view of corrosion in the different artificial lift systems. However, the main thing that I like to leave the message is that every specific system needs to be analyzed very carefully because the corrosion processes happen very different depending on the different artificial lift systems that we have. And as Rami mentioned, nowadays we are presented with a huge challenge that is the unconventional wells and those laterals that become a huge corrosion issue that I think I'm going to be talking a little bit about it. We'll go through the well completion, wellheads, flow lines, flow stations, gathering lines, and so on. So basically, I mean, for the amount of time that we have, it's difficult to be very specific of each one of these areas, because each one of these areas present different challenges from the point of view of corrosion. But hopefully you will learn to appreciate at least, and I'd like to plant that seed in many of you that you could continue in the area of corrosion. As you can see, corrosion is my passion. I've been going at it for 35 years. So hopefully you get out of here with that little seed. So the main objective is to take you through this journey, why it's important to have a comprehensive understanding of the complete production system. When I talk about the comprehensive understanding, we cannot be wearing blinders. If we want to control corrosion, and I'm going to talk about corrosion, but in a way, this has to do also with all the other issues in flow assurance. Because, I mean, at the end, it's the integrity of the specific installation, and the integrity is the whole corrosion, scaling, hydrate, everything. So, I mean, when it's focused on corrosion, but this applies to every other flow assurance issue, because from the point of view of integrity, I do not separate those. To me, it's as important understanding about hydrate formation, paraffin, asphalting, corrosion, scaling, slogging, etc., because they all affect each other. So, and this, when we have this comprehensive approach, this makes the integrity of the corrosion engineer a PE, an ME, a ChemE, an inspector, a guy that is going to be taking samples from the field. So because we have to have a huge understanding of everything that's going on, and also of materials, mechanics of materials, because we deal a lot with that. So why corrosion happens? First of all, quickly, corrosion happens first of all, it is a natural process. And it happens because we are taking the iron ore, which is resting in nature at its lowest amount of energy. Then we come and put a heck of a lot of energy in there. Boy, bunch of energy to produce a piece of pipe. That piece of pipe that we see there is full of energy. It's full of energy. And that energy is presented by charges that are on the surface of the material, internally and externally. So when we think about energy, if I go to a piece of pipe and I hammer it, that place where I hammer it is a higher concentration of energy. That area where I hammer is going to start corroding faster than the rest of the pipe. So when we go, for example, our drilling friends, they jog getting the pipes together. That area where we are damaging the pipe, that are areas where corrosion is going to start. And then we have the tubing. Oh, corrosion happened. Why did it happen? Well, because of, and I think, can we do something about it? Maybe we cannot, because it's the fact that we have a job turning the pipes around, or we have the pipes beautifully transported in trucks, and when they go to the field, boom, they dump them. Every location that that pipe hits a rock, areas where corrosion is going to start, and we will not know that, because we don't have the exact tracking of how things happen. So think about energy. Obviously, corrosion is an electrochemical process, which we have a lot of electrical stuff and chemical stuff, and they both compensate. So electrically, we can have a bunch of things happening, but if chemically doesn't happen, they balance each other. So one of the things that we have to do is what I always say, have a helicopter view of the system. Because it may be here, if we are wearing blinds to tackle what happens here in this gathering line, maybe I cannot achieve. I'm going to be spending a heck of a lot of money. While looking upstream, I could concentrate on how that separator is operated. Because it may be that I have water in my oil line because of a bad operation on the separator. Liquid carryover on the gas stream. And liquid carryover on the gas stream with water, corrosion. So looking always upstream is important. That's why the helicopter point of view. So ideally, blame it on the guy upstream. So if you're here, you blame it on the operator. If you're here, you blame it on the well services. And if you're here, you blame it on the reservoir. So we go back to the reservoir. Okay? So, but we need to understand what's happening in the reservoir. So that's where our journey starts. Okay? So starting at the reservoir, well completion and well operation. That's one of the things that we have to look when we look at well integrity. At the end, the word integrity means a lot. Means working as an integrated approach, as we were discussing earlier. It doesn't matter. In many companies, we see well services, not even talking to maintenance on the flow lines, not even talking to the operator on the flow stations. They all work in silos. I had the opportunity of working with the DOJ, the Department of Justice of the United States, due to the failure of the pipeline in Alaska that happened in 2006. Okay? And one of the things that that operating company was doing, that we all know who they are, but I'm not going to mention it, they were working in silos. And our objective through the DOJ was to see that they follow an integrity recipe, because it was part of the court, because they went to court. So they would follow an integrity process and work together within each department even. Okay? So when we talk about integrity, we have to be thinking what happens from the point of view of the organization. So starting with the reservoir. The reservoir characterization is important for us corrosion engineers, because we need to know how you guys are managing the reservoir. What are you thinking about it? Why would I care? Because in the ideal scenario, corrosion should start understanding the reservoir. How do we manage that reservoir? Okay? How is going to be developed? Because whatever you are thinking down there in your little cocoon is affecting whatever is going to be on the installation. How you develop that reservoir is going to be installation. Are the installations prepared for what you are thinking? Okay, so let's inject water to increase productivity. Then how about integrity of the installations and corrosion issues? And then all of a sudden, well, what integrity? What corrosion? What are you talking about? Yeah, we gotta be thinking what's going on. How is that reservoir managed? Have you ever thought about a corrosion engineer sitting next to the reservoir guy, or to see how things are? What is he thinking? What is he envisioning? And will those installations be accepting whatever he's envisioning? Never. You never think about that. But that's where things have to start. So, because when things go banana, then you go, help, what am I going to do? Maybe it's too late, maybe not. So reservoirs, we need to understand whether it's water-driven, combination, or gas cap. Why? Because I want to know when water starts in my completion, when the water is going to be in my completion, what's happening in this area, or from the point function of the fluids. Is it a saturated reservoir? Is it an undersaturated? It is a gas or retrograde condensate. Why do I care that? Well, because if it is a saturated reservoir, what's going to happen? That from the get-go, from right here, I may have issues of corrosion, because now I have free water with free gas and oil. Okay? When I am in undersaturated, okay, undersaturated, the oil goes in, maybe in an emulsion with the water, but still the gas is entrained in the oil. So the corrosion is going to be, a little bit controlled. But somewhere along, I'm going to have the bubble point. Somewhere along, I'm going to start having corrosion. So I need to know where I am in my reservoir to see how I accomplish from where I have. Or by the fact that the well is declining, I can be moving from an undersaturated to a saturated. When is that reservoir going to reach saturation? Because when that happens, I, as an integrity person, need to be aware of that. So here is some examples, okay? We have a declining curve, what is expected production, and as I go, I just mentioned, undersaturated, but as I go, becomes saturated, and then I have corrosion issues. And so, same thing with the, from the point of view of the characterization of the reservoir. So right here, when we sit with the reservoir engineer, that we are in the visualization stage, is where we can control more the corrosion as we develop this field. Because we know that this may never reach there. I mean, reservoir engineers, they do the best thinking, well, I'm gonna reach this production. That means that we as engineers have to define facilities to carry this huge amount of oil. But it turns out, oops, the reservoir guys made a mistake. It does not gonna reach here, it's reaching here. Okay, now I have this huge pipeline, it's a huge separator, and I'm gonna have a huge issues of corrosion. And that's what I need to know, because from the get-go, I can control even if I have a 36-inch pipeline with only 3 or 4 barrels of oil. I need to know that. So as we move from the point of view of water, as we move in time, of course, once again, to see where that water gets into the completion so that I can take action. Okay? So that's basically what I stated before. So that's all I have to say now for the reservoir. Now we move to the completion part. Now come our good friends, the drillers. Thank you for your job, thank you for your job, thank you for your job. Because then the drillers, they have this water-based mud with a water that they, who cares where that water came from? Was the water properly treated? I don't know. We just found that pond of water, and especially if you're drilling in Canada after winter, that water is all over. Oh, let's put water from here or from there or from the sea. And then that water from the sea, full of oxygen, full of bacteria that are not necessarily active, because the sea contains a heck of a lot of sulfur-reducing bacteria that are not active. But these guys make it wonderful. They stick it in there, it goes into the reservoir a little bit, no oxygen, bacteria wakes up, and Carlos comes because I got an issue of corrosion now. So, and imagine that with the unconventional wells and the fracking that we are doing. I did a lot of work in Canada, and it's amazing, and not only in Canada, in Montana, it's amazing how much the wells are souring, because in that huge horizontal section, bacteria love that environment to grow. And of course, from the get-go, they don't treat the water properly. But what, for the same reason I just mentioned. Oh yeah, well, we use chlorine dioxide. All right, chlorine dioxide reacts immediately, but it doesn't have any residence time. When it goes into the reservoir, no more biocide is in there. So we need to come with proper techniques to treat that water, and especially the millions and millions of gallons of water that we use in the fracking in the unconventional wells. So drilling, beginning on the reservoir with contamination because of the lack of treatment. So we can have corrosion due to H2S, especially when we're drilling containing H2S wells, that the drill bits can really make themselves brittle. Okay? Corrosion only on just on the torsion of the corrosion fatigue, erosion, general corrosion, corrosion even on the wires holding the towers, and the tower itself. So, I mean, this is all I'm going to talk about drilling, but in drilling, all that equipment is exposed to a lot of corrosion, a lot of external corrosion, and then I put that drill and go in there. I have a failure. What happened? Well, let's see the history where that pipe is coming from. Cementing, well, from my point of view, cement is the first barrier that we have for the casing. I mean, well, I was going to say, look at this building, not this building, but if we look at concrete structures, reinforced concrete. Reinforced concrete, the rebar in the concrete is well protected because of the cement outside. The pH of the cement, similarly to the cement that we use in the oil industry, is around 10 to 12 to 13. At that high pH, the rebar, the casing passivates, and therefore corrosion is somewhat controlled. But what is the quality of this cement? What is this cement completely all the way around on my casing? I don't know. So that is the first barrier. What is that quality? Because many of the cement is going to be exposed also to aquifers. So is that quality going to be protecting the casing externally? Okay. Then when I have the cement all the way to the perforations, I perforate, I'm cracking the cement. And I can have corrosion around the perforations. Okay. So also soil resistivity. When we talk about, I think I have a slide coming up to talk about that. But this is what I was talking about the pH. See, we are in the passive region. This is the natural potential of a steel. And between a pH of around 10 to 14, which is the pH of Portland cement, we are in this region of passivation. If we destroy that passivity, corrosion starts on the outside of the casing. Of course, outside I could say, well, I can protect it by other means. Here is an example of a casing. This is the cement. That what you see here is the wellhead. This happened in the north of Peru, in an area called Talara. In 1999, due to El Niño phenomenon, there was a huge mudslide. And that mudslide, well, carried mud, and of course, there was a well here with a soccer rod, went with the mudslide. So whatever was left was, this is the cement, and this is a close-up of the cement. The question is, was this cement cracked before the mudslide? Because if it was cracked, corrosion is going to be happening underneath. Same thing what happens in Florida on our bridges or in the US. Because we use salt, salt depassivates the steel, creates corrosion, and that's why we have all the bridges, the infrastructure of our bridges in the US are in terrible shape because of corrosion. And it's because of cracks in the cement that corrosion starts happening. So the question from a well is, how is the integrity of my cement? How well can I qualify that quality of the cement? So externally, we have corrosion due to the soil conditions, erosion due to the cement operations itself. When we are cementing a well, we are pumping cement down and outside. So is that how much there is going to be some damage on the pipe already? How about the soil? Different strata of the soil, these are different resistivity areas. Different resistivity areas can cause corrosion. Now let's think about electrical engineers. Different resistivities, if we go back to Ohm's law, those of you that remembers Ohm's law, different resistivity areas can cause different areas of corrosion. I can do something that is called cathodic protection, but externally, it's not easy. It is a challenge because of the different resistivity areas that you have. Okay? So the only barrier that we have is this cement that we have. I mean, think about what happened in Aliso Canyon. Aliso Canyon in California, there was a leaking methane leaking for about a year and a half or 2 years. Of course, Aliso Canyon was in one of the nice neighborhoods in California. People were getting sick, people were complaining. When they went to kill the well, it was not an easy operation. They had to sidetrack, etc. They finally killed the well, but the cause of the failure was corrosion because it was a section of the casing that was not cemented. What the heck are you talking about? Why are you needing a cement? Well, it was an old whatever. So, and the fact also that this was in a storage field, gas storage field, and when you think of a gas storage thing, you think of a big vessel that when they need gas for electricity, they open the they turn the key around,
Choke.
the choke, and there we go. And not only the choke, because they produce through the casing too. Since that happened, then the DOT said no more production from casings because it was internal and external corrosion that caused that casing. And we know that when we lose the casing, repairing a casing is not an easy task. So internal damage, as I mentioned, erosion due to the operations. It depends also how the well is completed. What happens with whether we have factors or not, okay? Because then we can be exposed the internal and external, the external surface of the tubing and the internal surface of the casing. If we, for example, we have a aqueous packer, what is in that water in the between the tubing and the casing? Was that water properly treated? Is brine? Oh well, brine is very conductive, so it's going to have a lot of issues with corrosion. But was it properly treated? Do I have a biocide? Do I have an oxygen scavenger? Do I have a corrosion inhibitor? I bet to you, probably not. And that's why I love my driller friends, you know, because it's not. Okay? Or when we do a workover, where is the water coming from when we do a workover? Anywhere. So are we treating that water? So, and also, when we use brines, of course, they affect the CRAs. So this is the important zone to protect, which we have the aquifer. Challenges in unconventional wells. We have, as I mentioned, we have been seeing much higher corrosion in the lower completion in this area. Why? Obviously, I'm here drawing, like we always draw the wells perfectly horizontal, which we know that's not the case. And we draw these perfectly vertical, I should have said, or perfectly horizontal, that we know that's not the case. Because they may go like this, they may go down or up. But this area of larger diameter than the tubing, 5 kilometers long or even 10 kilometers long, beautiful for sand to deposit, beautiful for liquid to deposit, beautiful for bacteria to grow. And all of a sudden, I'm getting a lot of sour. And that's one of the deals, one of the important things. In this job that we did in Canada, we've seen that even we could treat the water very well as we inject it. But as the well is produced, after a year or so, the well starts being sour and or increase the amount of H2S. Because how do you clean this area? I'm not an expert in petroleum engineering stuff, but I know that a coil tubing is not going to reach the end of a 10-kilometer for lateral. So, or I'm going to do a squeeze treatment. The squeezing is going to concentrate perhaps in this zone. It will never reach this area. So how do I get rid of that? So now we have beautiful technology with a lot of work for us, corrosion engineers. So that's one challenge. How do we clean this area? And that challenge I posted to university research. How do we clean those areas? How do we deal with this area? So I'm talking about SRB, but there are many other types of bacteria. So some of the challenges is lack of the correct water treatment pre-fracking. We normally use acids, gels, friction reducers, surfactants, but how about for corrosion? How about for bacteria or scaling? I know there is some research, some companies in Odessa that in the propan, they are using some biocides embedded into nanoparticles so that when they go into the fracking, as they are producing them, the inhibitors are going to be working for longer time. So that's an ongoing evaluation. You know? So how about the flowback water treatment? So fracking process, as I mentioned, we can get water from anywhere. Look at here. Look at all those type of bacteria. This is true data from one of those ponds in Canada. This Echerichia shigella. This is the family of Echerichia coli. That why? Because that is cow poop. Cyanobacteria, Enterobacter, Streptococcus, Marino, all these corrosion, Pseudomonas corrosion, and corrosion, they all produce corrosion. And we only worry about SRB, sulfur-reducing bacteria. We got plenty more that we don't even know. And this is before we inject the water into the wells. So the challenges, correct water treatment. And in addition, the challenge on the fracking, the water I can treat it very well. I can use oxygen scavenger. But then we go into the mixing table where we mix the water and the sand. That is open to the atmosphere. Oxygen gets in, then we inject it into the reservoir, and then we have a lot of issues for corrosion. Perhaps oxygen is what I would worry less because oxygen eventually is going to get consumed. But as it gets consumed, corrosion is taking place. So I don't know if there is a changing the fracking operations from the point of view of practical may be a challenge, and I haven't figured out how to do it, to get rid of the oxygen or the integrity of the laterals I mentioned. So that's a little bit on the well completion, okay? And I can keep talking more about it. Then on the wells, well, we mentioned from the perforations. Here is an example right there on an unconsolidated sand, okay? Right there in front of the perforation. That is like textbook erosion. Right in front of the perforations on an unconsolidated sand. Look at that, textbook, 90-degree impingement, and in the center with a little peak because of the way the sand was directly impinging there. Okay, so here, and you see that even it follows the perforation profile of the different holes of the perforation. I do apologize due to the precise nomenclature of you petroleum engineering guys. So naturally produced wells. When we think about internal corrosion, these are just a few of the variables that affect corrosion. I counted 36 factors. Put that in a mathematical equation to predict corrosion. I mean, it's like what you guys do for the reservoirs, that you gotta be, you know, because you got so many variables to characterize a reservoir. In corrosion, you have 36 variables that affect the corrosion rate. Try to put that in a mathematical equation. It's impossible because then asphalting, okay, oil, but this oil is different than that one, even from the same field, different formation, different type of oil, it is very difficult. So when we do predictions of corrosion rates, since we don't have a true mathematical modeling, we need a lot of experience. We need the input of experience when we do prediction of corrosion rates. So here is, for example, part of what I was mentioning. It's very important for me what many of the production engineers do. All the variables that they use to do their production engineering optimization. Pressure gradients, temperature gradients, velocity gradients, superficial liquid gas velocity, flow regimes, because those are minimal parameters where corrosion is affected by. Then I may have this type of corrosion behavior on a specific well, and from the bubble point onwards, because below the bubble point, all the gas is dissolved in the crude oil, and corrosion is basically negligible. Once the gas starts liberating bubble point, corrosion starts. Of course, with water. Outside the refineries, water is the main element for corrosion to happen. No water, I don't want to say no corrosion, but I say negligible corrosion because I don't believe there is never no corrosion. Inside refineries is a different mechanism, but outside refineries, no water, negligible corrosion. Here is an example of the flow modeling. This is a typical flow modeling. Here we have the water dew point, and this is data from a caliper tool that they did in one well in Peru in 2005 that I did some work in there. See, all gas. Water dew point, we started seeing, this was mist flow. We started seeing corrosion. And then as we go, this is the profile of the well. And as we go in this one, the flow regime changed from mist to a slug because of the inclination. Look at high corrosion rates. Here, almost 80%. It was a well that had a leak. Okay? So and this is production engineering stuff. That's why that coupling of the production engineering with the integrity is very important. Of course, as I mentioned, flow regimes. I mean, every single flow regime has issues of corrosion. Corrosion is very much dependent on the mass transfer process. So the higher the turbulence, the higher the corrosion rate is going to be. Even in our real, poor soccer rod well pumping units, where most of the flow is churn flow. Churn flow is very corrosive because it's very, the mass transfer, think about this, it's like this. That's a lot of turbulence, a lot of mass transfer, of course, but in shallow well, who cares? Let's take the rod out, put a new rod in, because it's only peanuts, but there is serious corrosion. In horizontal wells, a slug flow, terrible. Think about the sea. When you go to the sea, you're in Cancun. Oh yes, I'm in Cancun. Now it is 10 a.m. in the morning. The sea is flat. As the day goes by, then you start seeing the wind picking up. And as the wind picks up, then you start seeing the waves. And the waves could be, after around 3 in the afternoon, after you had quite a few beers, you try to go in the sea, and then the waves then will roll you. If you are with your kids, you go, oh, watch out because it's going to roll you. Same thing happens inside a pipeline. So the best multi-phase flow that is out there is nature. The Lord gave us a beautiful two-phase flow pipeline, the beach in Cancun, okay? So a slug flow not only produces high turbulence, but mechanically, think about a 30-inch line with a slug going by, and at the end it is an elbow. Mechanically, it's a lot of stresses to a pipeline. And those stresses are also high corrosion in those areas because it's that impingement. So from the point of view of production methods, as I mentioned, the soccer rods quickly, or there are soccer rods. I'm not going to have time to go through all of these, so I'm only going to concentrate on these top 3. Okay? Soccer rod pumps or Pcp pumps. In the soccer rod pump, we have a little deal going up and down, going up and down. And as the rod goes down, it goes in counter current with the fluid going up, higher turbulence. And in the coupling areas, there is a restriction of the cross-sectional area, higher velocity, higher corrosion rates. Okay? On the rod and as well as in the tubing. How about the gas on the annular space? This is wet gas. As we go up, water vapor can deposit on this area, affecting the internal corrosion of the casing or the external corrosion of the tubing. How about through the pump itself? Through the traveling valve to the static valve, there is a lot of corrosion because there are restrictions, and it comes with sand. This is a pump that, due to the drawdown, is going to be pulling sand also. So the sand is going to influence the corrosion rates. Okay? So that's what I, also oxygen ingress through the stuffing box. Hey, this is key, maintaining this stuffing box, because this same action of the rod can pump oxygen into the well. Or in many cases, production engineers say, well, let's open the casing, let's open it to atmosphere, I guess to reduce the pressure, to increase productivity. But the thing is that this level moves. When this level moves down, you are sucking in oxygen. When the level moves up, okay, so if you have a breathing well, now you have a breathing well, oxygen in, oxygen out, oxygen in, oxygen out. Oxygen is the worst corrosive agent that we have in nature. It is 80 times more corrosive than CO2 and about 400 times more corrosive than H2S. Oxygen is the worst. Lucky for us that we don't have oxygen in the reservoirs. We are lucky. But if we have oxygen in the reservoir, it's because we put it in there through the water treatment. Some of the water treatment that we're going to talk about, we gotta be careful not to get oxygen in, because during the water treatment, many of the equipment is open to atmosphere. So for sucker rod pumps, high local flow velocities at the couplings. So as I mentioned, high corrosion rates on the static valves on the pump. Here, and then the rod can be wearing against the tubing. What are you going to do there? There is no chemical that is going to help you minimize that. Well, but then we say, well, let's put a rotating device on the top that is going to be rotating the sucker rod. That is basically buying time, because that what's happening. I don't know if you can appreciate it. We are basically rotating the damage all around the tubing, which, okay, you are buying time, that's fine, but you are still damaging the pipe. Lucky that the rods are harder material than the tubing. So normally it's the tubing that suffers more than the rod itself. Inspections. Boy, I tell you, ladies and gents, when we started inspecting this simple visual inspection of the rods, it's amazing how much money we save the company. Here is the company man on the workover. Okay? The company man, he doesn't care whether the rod is corroded or not. Okay? He will put back the rod back into the well, only to find out that after a couple of weeks, it's going to be called back again because the well failed because of corrosion. He's going to be very happy because he's going to have a job. He's going to have a job because he's going to have a recurring every 2 weeks, every 2 weeks, every 2 weeks. Since we started doing visual inspection of each one of those rods, take them away, not go back into the well, we extended the workover frequency for 6 to a year, saving the company a lot of money. Not only doing that, these rods, I dare you to go to a warehouse of a company where they have the rods stored. They are just there, open to the atmosphere. Corrosion is taking place, and then you come to your well. This is a brand new rod, let's put it in. Whoop! The well failed tomorrow because it already was corroded. Think about that in a continuous rod that is in tension. If this holder breaks, that rod goes like a spring, ready to go straight. This is in tension, so you are in tension. Think of a paper clip. Okay, a paper clip. In that area where you put it in acid, that's the first area is going to corrode because of the tension, the stress that is in there. This is stressed already, exposed to the atmosphere. Look where this one was. Well, it's a brand new one. Then I go to my well, let's put a brand new rod, the well failed. Carlos, what, you are not doing your job because it's failing. Well, where is this coming from? That's why you have to then ride a helicopter to understand that when you buy these continuous rods from Weatherford, which are the ones who make them, you gotta make sure that in their shop, even when they come from Canada, in the ships are protected from corrosion because it's gonna go through, it's gonna go from Canada, perhaps running all the way through the Mississippi River, to the Caribbean Sea, to Venezuela or Colombia, and that trajectory needs to be well taken care of. So gas lift, is the gas lift dry? Does it have CO2, H2S? We may be corroding the casing. We may be, and in many cases we say, well, I'm gonna treat it with a corrosion inhibitor, but I don't have any place, so I'm gonna put the corrosion inhibitor into my gas stream. Very inefficient, but sometimes it is what we have. We don't have any other alternative. You know? Esp pumps, I love these Esp pumps. Here is a packerless well. So we have the motor. Of course, I'm showing here the motor perfectly in the center of the produced casing. We know that that's not the case. So if I move it a little bit, there is a little bit of space here where the velocities can be very high. It is a restriction. It reduces the cross-sectional area, higher velocity. That's why the motor casing is exposed to erosion and corrosion. And scaling, because this is the hottest part. It is the fluid around that is cooling that motor. So scales can be forming in that motor. But if those scales can be localized, producing corrosion on the deposit, or on the deposit corrosion. So I had a failure of a pump. Then we have goes into the intake, into a separator. Those are centrifugal separators. This thing is coming with sand, and that centrifugal separator is going to have a lot of erosion issues on that separator, and then the impellers through the tubing. So everywhere, and this gas, once again, externally in the tubing, internally in the casing. What is where in this gas I'm going to have that water vapor depositing in the form of free water? That's where I'm going to have corrosion issues. Okay, so here is one case. This is the inlet of a separator on an Esp pump. As you see, as it comes in, that swirling action to make it rotate, to separate the phases, to separate the sand and the fluid internally. So the sand is on the side, causing this. I don't know if you can appreciate the polished surface that is here. We almost lose the pump from the separator down. We almost lose it because it totally broke, but we caught it on time. Here, one characteristic when we have erosion is the polished surfaces. Here, this is talking about visiting the manufacturer. We mentioned about energies at the very beginning of the talk. I had to visit, that happened in 2001, the manufacturer of these Esp pumps in Oklahoma City. So you know who they are. Look what they do to the pipe. They have this lady with a torch on the piece of pipe. And this is a piece of pipe because internally they build the pump, they build the motor, they build the separator, they build it. So they have the torch. Why do they do that? Oh, because I want to straighten the pipeline. Okay, right. Then goes to another department. This is an old guy with a hammer. When it goes from here to there, they have already put the stators inside the casing, inside the piece of pipe. And this guy with the hammers, hammering away to align the stators inside the tube, the piece of tube. Look what they did. You see the marks of the torch here, and look at the marks of the hammers right there. I mentioned to you at the beginning, if I hammer a piece of pipe, that is an area where corrosion is going to start. And long and behold, This is a highlight of that. See the torches plus the hammering. And this is how we have the corrosion. What a casualty. Of course, here comes this guy from Venezuela telling those guys how to do the manufacturing of a pump. How can you do those things? You are damaging the whole structure. Of course, other manufacturers don't do that, but these guys were doing that. We even had to then recoat with a special metallic coatings all this stuff, and it didn't work very well. See, this is the highlight. Very deep. And there was a leak of the oil from the motor. Okay, I hope I'm not boring you. Okay? I don't. Just, if you need some toothpicks, I have a bunch of toothpicks around here, so if you need some. So then, drilling guys, completion guys, whenever you do a completion of the wells, please put a capillary stream down there. It doesn't matter whether it's not going to be used today, but eventually it's going to be used. And it is not true that you are going to convince management once that you are in the production of a well to say, hey, management, you know what? I need a workover to put that tubing out because I need to install a capillary stream to treat downhole. You know what management is going to say? You are fired. So please input it from the beginning in the completion. When you do a completion design it with the proper location to put capillary stream downhole. I'm doing some consulting job for a company in the Middle East. Every single well in this particular field has been completed with a capillary stream downhole. They are not using it right now because they are producing zero water. I don't believe that either, but they said it's zero water, but they don't have any corrosion issues. But they know that eventually they will because they are injecting water. So they have the completion ready for that. So please, it doesn't cost a lot more. This is peanuts compared to losing a completion, to losing a well. And at the bottom of the well, use a dispersion device. Chemicals work, ladies and gents. Corrosion inhibitors work. Scale inhibitors work. Paraffin inhibitors work. Asphaltene dispersants work. But you have to deploy them correctly. So please complete your installations with capillary tubing. So, see, here is the one case. This is the capillary. They have a little check valve and a elbow right here, a little elbow. Of course, one of the things when you leave this like this, with not a specific dispersion device, is that the solids coming in here can make that check valve to fail in the open position. When that happens, then the fluid going through it behaves as a pitot tube effect and sucks all the chemicals from the surface. So in the surface, you also need to have some proper devices so that won't happen, because that happened many cases, and I would blame the chemical company. You didn't fill the tank today. I filled it yesterday. Well, today is empty. Well, because it was because of that type of effect. And here is for ESPs, the capillary tube, they already come with the same armature of the electrical that goes to the electrical motor. So they are embedded in there. So don't think about it, just do it. So once again, we need a proper dispersion device because the chemical may channel, and you may be thinking, well, I'm protecting my equipment, and not necessarily. So that's why, because this is what may be happening. And then scaling can be happening because it's not mixing properly. So that's why you need a proper mixing device here so that the chemical mixes. And that's the key for every chemical to work, proper mixing. And don't ever do this, ladies and gents. I'm gonna treat it on what they call the backside. The backside means in the annular space. Of course, you need the well, first of all, to have no packers. But doing this, the same chemicals, especially asphaltene dispersants, are extremely corrosive because they have very low pH. Biocides have very low pH of 2, some of the biocides. Corrosion inhibitors may have low pH, but it's a corrosion inhibitor. How can it be corrosive? It can be corrosive. Scale inhibitors can be corrosive. So any chemical that we take can be corrosive. And then, let's assume that it's not. Are you really going to think that I'm going to have this magic chemical that is going to go all the way in countercurrent with the gas, going down? When it reaches the water, it's going to disperse in the water, very finely until it goes here and then up the tubing. Ah, come on, it's not going to happen. And this is what may happen from the corrosion point of view. Lucky for us, happened very close to the surface. But if it happens even further down, then you lose the casing. And then repairing a casing, I don't know, you guys know more than I do. I understand that sometimes you have to kill the well. Sometimes you may repair. Yes, sir?
Sure, but if it happened on the surface, it doesn't mean that nothing is damaged on the ground.
You don't know what's down here.
Yeah, that's what I'm saying. We don't know if it's damaged or not.
You don't know, but if it happened here, it very likely happened even further down. So in this case, it was repaired, but we have to run a log after repairing to make sure that the whole integrity of the well was good or not, because otherwise, it doesn't matter repair, just kill the well or do something else. So it's important to have a dispersion device. So need to complete wells, I mentioned that. CRAs, corrosion resistant alloys, ladies and gents, they are not immune to corrosion. Corrosion resistant alloys, they work very well within the specific integrity operating window. I have a well with no H2S. Use 13 chrome, no problem. Well, but now the well started to become sour. Say goodbye to your 13 chrome. Because the H2S and 13 chrome, they don't like each other. Or the salinity changes. If there is an increase in the salinity. Salinity is the enemy number, chlorides is the enemy number 1 of any corrosion resistant alloy. So they have their own integrity operating window within which they work very good. But that doesn't mean that you can sleep at night saying, okay, I'm not going to have corrosion anymore. Things change. Souring of the well, water changes, things change. Even duplex. Hey, our friends from Oman, if you look at the installations there, beautiful duplex all the way around. From the well, the surface, beautiful. And they have a lot of issues of corrosion on the wells. Because it turns out that when you are welding any corrosion resistant alloy, you need a specific process because next to the weld, you damage. A corrosion resistant alloy, the key of the corrosion resistant alloy is that it forms a corrosion product that is resistant to corrosion, but it corrodes. If you remove that corrosion passive layer, it's called a passive layer because the corrosion rock goes very way down. But if you remove it, it can be as corrosive as carbon steel. It can corrode as fast as carbon steel. So in that specific case, what they did is that when you are welding that, you are removing that passive layer. Externally, it's not an issue because you come back and refresh it and rebuild that passive layer. But internally, how do you do that? So now you have a beautiful material, expensive corrosion. So wellheads are the most hydrodynamically unfriendly equipment in the oil and gas operations. It's just a bunch of valves. This is truly 90, and then we have the chokes. And depending on the conditions of the chokes, hey, we had wells with 10,000 psi. Here, 12,000, 10,000 psi and 1,200 psi downstream of the choke. Imagine the huge velocity across the choke. Mach 1 velocity. No matter what you do there, is going to destroy the chokes and the choke box, as we see there, as we see that. And even the choke box, that is a massive amount of steel. By this choke like that, it goes anywhere, and then you have a mess there. Multi-phase flow line, now I'm out of the well. Beautiful challenge. This is, in my experience, and this was one of the biggest challenges to manage corrosion in multi-phase flow. Because of the hydrodynamics in them, the turbulence, and sand, and bacteria, and water. So now they came out in that particular field, they came up with a wonderful idea. Let's have a centralized processing facility for the oil. Here it is. This is the centralized processing facility. We have a multi-port valve here collecting fluid from different wells from this area, and then from this area, and then from this area. 16-inch pipeline. The flow here was stratified flow, barely moving. Here, because it's an incline, stratified slope and slope, very high corrosion rates. And as I go, the more fluid goes into the line, and this area, the pipeline was almost full. No corrosion. From here, terrible, here, terrible. Go back to the same. The flow, very low flow, very localized turbulence. So sometimes you gotta play the doctor and to listen the flow regimes on the pipeline. So really, this is just to listen to see, to corroborate if the modeling was correct by listening of the frequency of a slugging going back in the pipeline. So things to consider that are flow related: the effect of emulsion, saran, wettability. Who's wetting the pipeline? Is it the oil or is it the water? Very important. I remember when I was a student here that Dale Peters, I don't know if he's still around, he had a project looking at the hysteresis of the crude oil and the wettability. This is big now. There is a huge research going on right now in PRCI, trying to understand and come up with equations to predict the wettability. Demulsifiers means free water. Operations would love to have demulsifiers as far upstream as possible. We don't, because the farther upstream, water is going to separate and I'm going to have corrosion. I'd rather have an emulsion rather than free water. But of course, operators don't like that, and emulsions to transport an emulsion is not flow assurance friendly. The amount of water, is the water scaling, and flow velocities, as I mentioned all throughout. Here is the case. Remember that mention about the slugging? This is in Alaska, 36-inch line. Due to a slug, in Alaska, all the pipelines are above ground because of the permafrost, okay? And insulated. And because of a slug, just knocked it down from the supports. So that tells you the huge mechanical issues of slugging. Alaska is a particular deal because when they designed the field of Alaska, of course, the production was at that time very high. That's why you have these huge pipelines. But they all insulated their lines because of the cold weather. But you know what didn't they do? They did not coat underneath the insulation. Guess what is the biggest trouble that Alaska has right now? Corrosion under insulation. Not even internal, corrosion under insulation. They didn't think, because they said, oh, well, Alaska is an Arctic dry environment. Yeah, but they forgot that the snow melts in summertime. And if the jacket is not well protected or has defects, water gets into the insulation, causing corrosion under insulation. Anyway, geometry is very important. We were talking about turbulence. That's why when we are designing systems, that's where we have the most powerful tool in the design to control corrosion. Okay? Avoiding elbows, changes in schedule, uphill, downhill, dents. Here is the case of a multi-phase line with a temporary forever type of repair. Look at that. So this becomes a clamp duct instead of a duct line, a pipeline. So this is multi-phase. That was that 16-inch pipeline that I mentioned before. Why? Because look, the fuller the pipeline is, I have a slot film thickness thicker than in this case. Look at the turbulence. Think about when you go into the sea. When you go into the sea. I mean, there is a wave. What do, dock? And the further you go down, the wave passes by, not an issue. But if you are close to the shore, the slot film thickness is like this. There is no way to hide, and you'll see how the sand is all shook. So that means that the fuller the pipeline, if I have a slot flow from the point of view of mass transfer on the bottom of the line, is better because there is less mass transfer than if the slot film thickness is smaller. Simple things like that one. Here I quickly wanna show you, I don't know if I'm gonna be able to get this going here, yeah. Well, it's not gonna work. Well, this is a video of a slug, it's not working. So I mentioned that that's the type of corrosion. See, this is 9 leaks, 5 leaks, 9 leaks, 0 leaks, in that line that I mentioned before. It is the type of corrosion that we saw. Here we see, which direction do you think is the flow? Is the flow out of or into the screen?
Towards us.
To look into the screen. Look at the shape, U shape, U shape, U shape, pointing in that direction. So that's one morphology that helps you identify, see, depending on the U shape that you're forming. So it's going into the screen. Here is a highlight. Here is another. It is very difficult when you have the dead body, like this one, to say, okay, what did he die of? You need to do the autopsy. You need to do the proper research. Okay? Yes, madam, it's true. Because if I look at that and say, well, this happened because of that corrosion, that's not true, it's impossible. However, there are certain morphologies that can lead you to believe one way or another, and one of them is this one. This is very typical of CO2 corrosion. However, you cannot conclude until you have all the evidence. Okay? Yeah, you may be thinking, well, maybe I should have been, today's Friday, I should have been down there in the beach somewhere. So here is the beach somewhere, and this is the best schooling for multi-phase flow. See? Understanding the seed. You sit there at 6 a.m. in the morning and start seeing the wind and the interaction of the wind, and see the shape of the bay. Doesn't that relate a little bit of the shape of this? Okay. Right, tips to conserve the mechanical integrity. So the most difficult equipment is multi-phase flow. Constant pigging, scraping is key to maintaining the integrity. Brushing your tooth to avoid bacteria. Many chemicals, biocides, scale inhibitors, corrosion inhibitors, surfactants. Maintaining the pipeline as full as possible. Avoid oxygen ingress at all times. Avoid the ingress of fluids from pits. From pits meaning the open pits, discarded oil. Pigging is the most important to maintain the integrity of pipelines. Okay? Pigging doesn't necessarily mean that you are removing a corrosion inhibitor. They would not. But normally we increase more the corrosion inhibitor. Here is an example of why pigging. Every one of these dark bars, pigging. Here is without pigging, high corrosion rate. Started pigging, low corrosion rate, low corrosion rate, low corrosion rate. They didn't pig this, high corrosion rate. So pigging works. to reduce the corrosion rate. Pigging, this is an example of in Campos Bay in Brazil, in the north part of Rio de Janeiro. Of course, they were pigging not for corrosion purposes, but for liquid loading. They had a lot of liquid in the gas lines, so it was affecting the production upstream. So they use a lot of spheric pigs, these pigs, to remove the fluid. As a matter of fact, the correlations that are in the pipe phase for this type of pigging came out of the PUFFP projects, because there was a Brazilian guy working on it. That wasn't during my time, if I remember. So, and this pigging facility, the nice thing is that it does it automatically every 4 hours. They have this in, as you say, in incline, so it automatically opens the valve, drops the ball, it goes to shore, and onshore, you pick it up here, and they have it. They do that every 4 hours all around. Here are examples of some pigs. Here is in a water system. Here is this is black powder, iron sulfide, in a gas line, and this is after hydrostatic testing. Pieces of wood. The only thing I have not yet seen inside a pipeline is a human being, but I have seen hard hats, boots, rabbits, snakes, you name it. Okay? So, but this pigging is very important, because you see, if you were pigging normally, this debris is what you want to collect and do the analysis to see if you got bacteria, to see what is it that you have. Okay, so quickly, flow stations, and I'm going to go quickly because I think I am way out of my time. We go back to the separators. Why is the separator so important to maintain a good operation of the separator? If we increase the level, or we have sand in the separator, increases the level. If I increase the level, the water level rises. If the water level rises, there is more water into the oil. I don't like that. If the water level rises, the velocity of the flow is higher, then I'm going to have more oil into the water. We don't like that either. And if this level rises, I'm going to have higher velocity through these baffles. Then baffles are not going to collect the mist of the liquid, and then I'm going to have liquid carry over, because I increase the cross-sectional area. So therefore, I have issues of corrosion. So those are things, that's why we need to focus also upstream, as I was mentioning. So pipelines. We have in the world about 92 times the amount of pipelines to go around the earth. 92 times, more than that, because this is a few years old when I did the research. 70% of those lines are not piggable, because we said dry gas, dry crude oil. There is no such thing as dry gas or dry crude oil. So that's about why not piggable, the misconception of dry gas and dry crude oil. Here is a failure that happened in 2002 in Carlsbad, New Mexico, that killed 12 people. Dry gas line. Dry gas means somebody upstream is dehydrating that gas, removing the water vapor. What is the reliability of that plant upstream? Can I trust that it's going to be 100% operated, or that the operator is probably, one time the operator is doing like, shut down, because he dropped the phone on the shutdown switch. Hey, it happens. So I cannot rely on a dry gas being free of corrosion. Dry crude oil, this is what's happening in Alaska. Dry crude oil. What is the definition of dry crude oil? Less than 0.5 BS&W. BS&W stands for base, sediment, and water. Okay, but if I am producing 400,000 barrels of oil, that is 2,000 barrels of water. Is that water going to be in an emulsion? I don't know, because that depends on the characteristic of the crude oil. I mean, in Africa, there are some crude oils that only with 5% of water, just as the oil spits them out, not necessarily in an emulsion. So it depends on the characteristic of the crude oil. And we have the leak, and this leak happened due to microbiologically influenced corrosion. Bacteria by itself, I mean, we have, also, anybody cooks here? Anybody cooks? Anybody makes bread? What do you use to make bread? Yeast. And you keep the yeast in your refrigerator, or you buy it in the supermarket. That is bacteria. You put it in your hand and they don't jump, they are there, right? And that bacteria become active when you mix it with water. And when he mixes that yeast with water, why is the bread lifting? Because it's producing CO2. Oh. So the bacteria may not be active until they see the water. See? Here is the case when we dehydrate, we depend on a dehydration plant. So now we can be operating in this area without no water, hopefully. But it depends, because I could operate in this area. This is the water dew point line. If I am operating here, I shouldn't have any water. But if I operate from here to here, oops, at this point in my pipeline, I'm gonna have water. And see the beauty of the flow modeling. I know where this can be happening. Then I know where exactly corrosion is going to start happening. The beautiful of the flow model that you guys use in the oil industry. Okay? Water condensing right there, and I know I can find that out. That is the beauty about the hydrodynamic simulations. Scaling tendencies. Why? Because they depend on pressure and temperatures, pH, paraffin, because of the cloud and pour points, temperature dependent. And then I know how is my temperature behavior throughout my whole field. I can know what is my velocity throughout my whole field to see if I have erosion or corrosion or both, or asphalt information, because the RMA is very much dependent on pressure. Through a colloidal instability index, for example. Hydrate formation. I hear you have here a hydrate research facility. Hey, hydrate, pressure, and temperature. So beautiful. I mean, we have beautiful tools. So, the end of the journey, or is it? Or is it? Because then we have another beast further downstream, and that is refineries. That is another world and another journey. So, and we only discuss internal corrosion. External corrosion is another journey. So, it's a serious business. Thank you for your attention. So, thank you. Any questions?
So when we're talking about corrosion, we're talking about the phenomenon, and one of the phenomena is protective scale formation. People say in the literature. But when we do pigging, don't we also damaging that protective scale formation?
Okay. Yeah.
If we do, isn't that mean that pigging should be continuous operation? Because every time when we do that, we destroy our protective scale that's inside the pipeline.
Number one, I don't believe on a protective scale from the point of view of corrosion. Okay. There is no, if you can guarantee to me that you're going to be forming a protective scale from that beginning of the line to that end of the line, you cannot. Okay? So pipelines generally you would kind of go more to the protectiveness of a corrosion product into a well, but on pipelines that doesn't happen that basically. Pigging doesn't necessarily, unless you use a brush pig, okay, then it's going to be damaging that scale, assuming that you have a protective scale, which my experience tells me I don't believe in that, okay? If we use many of the prediction equations that are in the literature, they have a scale factor that goes down depending on the temperature. Okay, well, okay, but I don't believe it. And because I don't believe it is because in those locations where there is not going to be that so-called protective scale, then you're going to have very high corrosion rate because of the pitting. Okay? So, and also, people say, well, but I have a paraffin. Paraffin is going to stop corrosion. Yes, definitely. Can you guarantee that I'm going to be forming a very nice paraffin layer through a pipeline, or a nice asphaltic layer, or a nice calcium carbonate layer? Calcium carbonate is marble. We use it in our houses for the floor and decorative stuff. As you can see, it's very hard. But if you can see, it is porous. It is porous. So through those pores, hydrogen can permeate and cause corrosion anyway. Okay? Any other comments, questions? Yes, sir.
So I remember you showed the multi-phase pipeline where we had several wells on the left side.
Yes.
They were connecting to the one pipeline and they were going to the right to the refinery. And you told that we have more corrosion happening on the left side, the stratified vapor region, than in the straight line on the right side. But why it is like that? Isn't the water inside the pipeline connected to the lower side of the...
In all three cases, the water is connected to the lower side. But then you gotta be thinking of what's happening at the pipeline wall turbulence. Where is it suffering from higher turbulence? When the pipeline is fuller or when the pipeline is less with less fluid? Because when it is with less fluid, any little change in the topography of the line is going to change the flow regime. And as I mentioned, the slug film thickness, meaning that the piece of water that is going to be there, is so small that whatever turbulence I have is going to bring the corrosive species from the environment towards the pipeline wall much faster than if I have a higher slug film thickness. Then whatever turbulence is happening here, but here it's not happening as much. Am I going to have corrosion? Yes, but it may be more of a generalized corrosion than a localized corrosion that you see in that side of the pipeline. Because as you see, there were pits.
So in that slide, you meant that all your three phases are mixed with each other.
The multi-phase flow, not necessarily mixed. They will be separating as they go because you have water, oil, and gas.
But isn't water will be always in the bottom?
It's gonna be always in the bottom, definitely. Yes, but no matter if the water is always in the bottom, but the thickness of the water is higher, whatever turbulence is happening away from the pipeline wall. Think about mass transfer, because corrosion is an electrochemical process, but the chemical process is controlled along with the mass transfer process. So think about mass transfer. That's why I always said, if you can design an installation that is hydrodynamically friendly, you are not only controlling corrosion, but you are also controlling scaling, you're also controlling paraffin, you're also controlling any other flow assurance issue.
Challenges when you design it, you don't know what operates.
Well, you do your best.
You do your best, yeah.
You do your best, and of course, you design in some premises that your reservoir engineers tell us.
All right, we've got maybe time for one more question. Besides Shamka, you can converse offline.
Okay.
Any other questions or comments? Well, if there are no other questions, go ahead.
Okay, so we have a lot of articles and tools to measure corrosion. What do you think? How far are they from being ideal, or is there something to be ideal and measure corrosion precisely? Because I read a lot of literature and
No, I know. Well, my take on that, I even have my own corrosion, my correlation to predict corrosion, and whenever I run it, I pray a lot that I'm going to nail it. And my experience in that is that all of those corrosion rate correlations, they over predict corrosion rate, and they throw you into a conservatism that is not necessary. And that's the misconception with many of the engineering companies that I have had the opportunity of evaluating projects for different parts of the world from many of the big names that are in the energy corridor in Houston. That you have the engineer, they run a software, let's say they run shell software, corrosion rate right here. What am I gonna do? Duplex. Oh, of course, duplex. And that's easy, okay? But then when you go with experience, what do you mean duplex? I run a field exactly like that one, and carbon steel was beautiful, so they all overpredict corrosion rate. So you have to understand how is the hydrodynamics, what is the experience in there, what experience do you have? That's why I said in my slide, those corrosion rates cannot be given without the help or without the input of a subject matter expert, because otherwise you are going to be over designing the rest of your life. Of course, you are going to perhaps cover your work because you are over designing, and by the time it corrodes, but it doesn't make sense that you make the company spend in duplex when it's not necessarily duplex, and you can do perfect with carbon steel, for example.
Okay, so when we talk about,
If you don't stop this guy, you
Yeah,
continue.
One more.
okay, when we're talking about corrosion measurements, are you thinking that linear polarization resistance tests and impedance tests are more advanced and precise methods to measure them in experiments?
Linear polarization works only when you have very clean waters. That's it. In the lab works fine. If you're doing it to a lab, fine. In the field, coupons are weight loss coupons. Basically, you stick a piece of metal today and take it out after so much. Because of the weight loss, you can calculate a corrosion rate. Coupons have been around since the dinosaur era. Okay, so whenever the dinosaurs were in, they put coupons in pipeline. I love them because they give you a nice morphology. Let's put it this way. When we do monitoring of corrosion, however we use, it's like learning a new language. Where are you from?
Azerbaijan.
Azerbaijan. I do not speak Azerbaijani. I have been there though, but I don't speak Azerbaijan. But I bet to you that if I spend 1 year in Azerbaijan, I will end up speaking Azerbaijan. You need to learn to understand what is it that specific system that you are putting in and that specific pipeline is telling you. Pipelines don't talk. We are the doctors. When we go to the doctor, we say, well, I got a pain here, a pain here. Pipelines definitely don't talk. So they are speaking to you in a language that you have to learn to understand them before you can say, oh, I have high corrosion. Well, let's see next time. And then once you learn the language of that specific patient, you make sense of what's going on. Going back of the type of monitoring, coupons, electrical resistance probes are what is mostly used in the field. Electrical resistance probes can be adapted to any environment. Coupons also to any environment. The two compensate each other. Coupons, you put a coupon today, and then you take it out after a month. What happened in between, you don't know. But electrical resistance probe can tell you, I mean, when you do a well stimulation, if you have an electrical resistance probe on the surface, in the acid flow back, you're gonna see a peak. And then when you see that peak, if you connect that to your SCADA system, beautiful. But if the workover person who did this stimulation did not inform you, the corrosion guy, that was done, then you have to figure out what happened here. So now you have to do your due diligence to say, okay, what happened? Well, it turns out that Mr. over there did a workover and we were not informed, and that's why we have these peaks. Okay. But those two are the ones that are mostly used in the field. There is no one single monitoring device that is 100% reliable. Monitoring is key to manage not only corrosion, all the flow assurance issues that we talked about. Inspections, monitoring are leading indicators. Inspections are lagging indicators because the inspection will tell you something after the fact has happened. Is it too late? No, it's not too late, but it is a lagging. So monitoring is key to manage everything that we talked about and flow assurance issue. All right? But linear polarization and electrochemical noise, forget it. That's only in the lab, works well.
Right, let's give Dr. Palacios another hand. Shall we do the raffle?
Oh, let's do the raffle. So we have everybody staying here?
It's not too late if you want to put your name in there to draw a copy of the book.
We need an innocent hand. Are you gonna write your name?
Yes.
Okay. Yeah, go ahead.
So, I want to ask a question about carbon capture and storage systems from a carbon point of view, because I'm planning to do simulations, and simulate carbon capture and storage. I might be and do carbon PCR test and impedance. And I was thinking that will be right. I think that's a cost.
One of the things you will check is presence of, like, NOx, SOx, right? Those type of things as well.
Influence of the impurities on the corrosion rate.
Well, in a lab type of field, yeah, you can do it. But remember, you have to have clean lab. But that's what I'm saying, in a lab, you can do that. And in the mechanical engineering department, when I did my thesis, there were some autoclaves, okay? Those autoclaves should be somewhere